That's on your screen?
No, on my screen there's all black.
Nothing on. I see it. No. Oh. Oh.
Okay. So you can, I think, relax a little bit. Can't hear you. Be quiet. Okay. It's okay. Perfect. So now you can probably relax a little bit because you're all familiar with the topic. Binary search. It's really old and it's essentially so old that already the Babylonians used it, at least some kind of some intuitive form of it. There were some tables found with reciprocal values, and the pairs were ordered so that instead of computing them by hand, you can find them by, as I said, an intuitive form, like in a phone book, of binary search. So, and indeed, binary search is hopefully known by every computer science student. We teach it in every algorithmics course. And yeah, so let's have a look at two examples of two definitions of binary search. So the first one is from Donald Knuth from The Art of Computer Programming, and it's along the following lines. So assume we have a table where we have keys k1 to kn, and we assume that they are sorted. And now, given a key k, we search for an index I such that ki is equal to our search key k. So that's the problem description. And now, how is binary search performed? So we pick an index between 1 and n, and we compare k to km, and there are three possible outcomes. So the first outcome is k could be less than km. In this case, we eliminate the keys km from kn from consideration, or we could be lucky and k could be equal to km. In this case, we are done. Or k could be greater than km, so this is the dual case, so the first one, in which case we eliminate the keys k1 to km from consideration. And now to the binary part of binary search, if we pick the m to be the midpoint, then we get logarithmic running time. So that's one definition. Then a second one from Introduction to Functional Programming by Richard Burt and Phil Wadler. It's a bit different. So now here we have again, and I forgot, of course, to say that we recurse then, in this case, after some possible re-indexing, and in the base case, well, that's trivial if we have only one element. So now, Introduction to Functional Programming. Similar, we have an interval L to R, and now we have a predicate P. So I'm using Agda syntax here, so we don't go from n to bool, but from n to set. So, but we search the smallest index I in L to R such that Pi holds, and of course we assume that P is monotone. And so again, that's the problem. And now how is the algorithm? We again pick an index m in the search interval and we check PM. Now there are two possible outcomes. Either PM holds. In this case, we eliminate the indices 1 plus m from R from consideration, or PM does not hold. In this case, we eliminate the indices L to m from consideration. And again, for the binary part of binary search, if we pick m to be the midpoint, we get logarithmic running time. Of course, there are many differences between those two definitions, but there are also, they share some points. Of course, the binary part, choosing m to be the midpoint, Also, we proceed, of course, recursively. And also, in each recursive step, we eliminate roughly half of the search space. And I think most importantly, both assume some kind of monotonicity. So in the first one, we had that our keys were sorted. And in the second one, we assume that our predicate P is monotone. So now you can open your favorite textbook describing binary search, and probably the definition there will be somewhat similar to one of these definitions. And now you can go a bit further in the textbook and open the exercises for this chapter, and you might find the following exercise. So, the following exercise: you are a contestant on the game show Beat Your Neighbors. You are presented with a sequence of n boxes, each containing a natural number. It costs 100 euros. To open a box, your goal is to find a box whose number is larger than its left and right neighbors. If you spend less money than any of your opponents, you win a week-long trip to Berlin. Actually, this exercise is from Jeff Erickson's book on algorithms, and it's not on the part of binary search, but this sounds better than saying find a local maximum by with as few lookups as possible. So, but there are textbooks that have such an exercise for binary search. However, this does not fit the definition of binary search. So the reader is, of course, expected to adapt binary search to this exercise. So let's try to solve this on an example. Assume that these are our boxes. And of course, we have to say what happens at the very left and very right. So we assume that we have virtual boxes containing 0 at the very left and very right. And of course, we say that greater is greater or equal. So now let's draw the values, and we are interested in a local maximum. So actually, for a local maximum, the only thing that matters is the slope, not really the absolute values. And now, why is there even a local maximum? Well, we assume, because we have these virtual boxes at the very left and at the very right, that the very left slope is non-decreasing and the very right slope is non-increasing. So in between there must be a local maximum. And now let's just look at the middle slope, and now it's again decreasing, so we know that there is again a local maximum on the left side, and we do the same again. We look at the middle slope, and then we are done in the end. So we have found the local maximum by binary search. And so for understanding why this works, let's have a look at an even simpler example, which is very, very similar. So here we have the task of finding an even odd pair. So we have given these boxes here, and the task is to find an index I such that the box at position I is even and the value at 1 plus I is odd. And this actually fits the description of binary search we've had earlier. So we have a predicate that's monotone. In this case, the predicate is odd. It's a bit different in this case, since we are looking for a pair, but this shouldn't bother us. So let's perform binary search. We look at the middle value, and it's even, so we remove the first half from consideration. So now we look again at the middle value, and it's odd, so we remove the second half from consideration, and so on. And in the end, we find the even odd pair. So let's do this same example, the same values again, but we shuffle them around. We have now no monotonicity given. Nonetheless, we just perform binary search as we would before. So we start at the middle. We have 5. 5 is odd, but we can't talk about anymore about removing the right half from consideration, because obviously there are 2 even odd pairs at the right half. Nonetheless, we just go to the left half as we would before. We look at the middle value here. It's 10, so it's even. Again, we can't really talk about eliminating left half. There's again an even odd pair there. Nonetheless, we go right and we perform the binary search and we find the even odd pair. Why did this work? So did I just choose a good example? So let's formalize this in Agda to make sure that this really works. So we have a function, even odd pair, which takes our interval L to R. We model our boxes as functions from n to n, and we promise to return an index I such that box I is even and box 1 plus I is odd. So let's first make the recursive step. We model our search interval by a tree, but so we have this M is, you can think of M as the midpoint, T is the left half, and U is the right half of the interval. And we check now the parity of the box in the middle, and there are 2 possible outcomes. So it could be odd. In this case, just by our recipe, we go left, and if it's even, we go right. So so now let's look at the base case. In this case, well, we can't recurse anymore. We have to return something, and we can't pull the rabbit out of the hat. So the only possibility is that we assume that the box at position n is even and the box at position n plus 1 is odd. So we assume this here. So we assume that the leftmost box is even and the rightmost box is odd. And in the base case, we just return this. And in the recursive case, we have to adjust a little bit, but that's exactly what we are checking here. We check the parity of the middle box, and now we have this. We have that the middle box is odd, so we go to the left one, and now the rightmost box is odd, so we can recurse. And so what we have here actually is a very simple example of an invariant. So we start with our boxes. The leftmost box is even, the rightmost box is odd. We look at the middle box. If it's odd, we go left. If it's even, we go right. So we maintain the invariant after we have looked at the box at the middle. And in the end, if we have only 2 boxes left, then the invariant gives us already the result. And actually, that's exactly what's also happened with the beat your neighbors example with the local maximum. So in this maximum here, we were guaranteed to find an even odd pair, and for the local maximum, this was the case as well. So, and we can now abstract away from even odd or local maxima. We can say binary search is the following function. We have an interval L to R, and now instead of looking for even or odd or for the sign, we have just any oracle, and we have any 2 predicates P and Q, and they don't have to be even exclusive, just any 2 predicates P and Q, and this decision procedure oracle, and we assume that at the leftmost point L holds and at the at the leftmost box, or at the leftmost point, P holds, and at the rightmost box, Q holds. And we promised now at the end that we return an I such that we have Pi and Q1 plus I. And the code below is really the same as for even odd pair. We just rename, and we have Oracle now as an extra argument. So you see that we don't eliminate anything. We just go where we for sure find a solution. So we think positive, therefore the title. And we don't assume monotonicity. So binary search has nothing to do with monotonicity. That's the point here. So why then why almost all definitions of binary search assume monotonicity then? Let's go back to the very first definition from Knuth, where we have the problem of table lookup. So how does table lookup look in this new framework? So again, we have an interval L to R, and we model our table as just a function from n to n. We have our search key. And now, instead of looking for equality somewhere, we first, we promise to return an index I such that table I is less than or equal to key, and key is less than table 1 plus I, provided that key is greater than the leftmost point and less than the rightmost element. So in traditional binary search, we search for equality, not for two inequalities. We want an I such that table I is really equal to key. And of course, it might be the case that there is no such I. It may fail, so we have actually a decision procedure. So in this case here, we always succeed, but we somehow give less. So, but we didn't assume monotonicity yet. So let's assume monotonicity. And so the only thing that we add here is monotonicity. And now we can actually decide if there is an I, such that table I is equal to key. And the idea is pretty simple. So table I, we have this, we have this proof here, table I is less than or equal to key, and now we look into this proof and we check. If it's really an equality proof, then we are already done, so table I is really equal to key, and if table I is strictly less than key, now in this case we use monotonicity to rule out that there is nowhere such an index I such that table I is equal to key. So monotonicity is actually only used in a post-processing step. It's not really used for binary search. So let's wrap this up. So in traditional binary search, we look for a single index, but actually what the right way to do is we should look for a pair of indices of two predicates rather than only one predicate. And we don't rely on monotonicity, but really on an invariant for the leftmost and rightmost point of the search interval. And we don't eliminate, so monotonicity allows us to eliminate, but actually that's not the right way. You should think positively and focus on where you can find the solution. And therefore we are always successful in comparison to traditional binary search, which of course may fail. So, as the conclusion, binary search has nothing to do with monotonicity. It's about this invariant, so think positively. Thank you.
Great, thank you, Alexander. Let's take some questions. So, am I right in thinking that kind of one of the key things is defining this interval, because that seems kind of important with the between L and R. Like, it seems important to then kind of understand the relationships and the underlying data, right? Because in the beat your neighbor, in the odd even case, you could have a data set which was sort of all odd or something like that, right?
Assume at the first place that you have so that you at the rightmost point is odd and the leftmost point is even. You could of course check this before you run binary search, and I mean if this doesn't hold, then there is no point in even running binary search.
Yeah. So the assumption would be false, and then yeah.
That was my question.
Right, okay, great. Next question.
Maybe I'm trying to ask the same thing. In your first two examples, they differed by the worst case was so logarithmic was the worst case in the first example, while all the cases were logarithmic in the second example, right? In the beginning of your talk. So can you say something about best case and worst case scenarios and average scenario for your version of binary search?
I mean, this version of binary search, okay, I didn't talk about the interval representation here. So actually, the only thing about the binary part and the logarithmic running time is only running time improvement. So here, if m is really the midpoint, which this type in this case doesn't really force, but if m is the midpoint, then we have logarithmic running time worst case as well. Yeah.
Okay. Any further questions?